Hey everyone, second try in this video. Originally it crashed, so fingers crossed this one goes fine. Um, this is our first 8.1 problem, so I'm going to try to give you a really detailed walkthrough of how to do a problem like this, point out everything I possibly can that'll help you out on something like this, and give you a guide for the future. I'll be doing a few things here that I'm trying to help you not just on this problem, but on all the problems. So I'll be doing a little bit more than I'd even expect of you. So what we have here is we have some sort of puck, and it is going up this ramp. Now the ramp right here is pushing the puck away from the surface, so the puck goes up the ramp. And what we need to do is we need to keep track of the energy in the system, where that energy is moving, how that energy is being stored, and how that energy is being changing. Um, this problem, I'll actually answer it two different ways, or at least I'll show the LOL diagram two different ways. One of them is much more useful. So we see here that the puck originally is moving, and I know that moving is a way of storing energy. So I'm going to go ahead and mark here that this energy is energy stored kinetically. And I'm going to go ahead and put in some boxes for that. I'll do 4 boxes to start. And then later I can see from the problem that we're going uphill. So usually that means it's going to be convenient for me to show energy stored gravitationally. Because we're moving up, we're applying a force against gravity. And if we're applying a force against gravity, that work we can be described as being stored gravitationally, and that's going to be convenient in the future. Now, I'm not going to start off with any because we haven't gone up the ramp yet, but later we're going to go up the ramp. But this leads us to an important point. We have to pick our system. And the rule is we have to, all this energy that we are going to put in this diagram has to be stored in the objects that we call our system. So for example, here, this energy stored kinetically is stored physically in the puck. So the system must include the puck. All right, this guy right here. And then later, it's going to be going uphill, and we're going to be saying it's stored gravitationally. Well, energy stored gravitationally is an interaction between the puck and the Earth. So we have to include the Earth. After we're done this LOL diagram, I'll actually show you an alternate version of this that works out just fine. That does not include the Earth, but it just means that we can't use energy stored gravitationally, which ultimately will make it less useful. But for now, we'll stick here. There will be energy stored gravitationally, and that means we have to include the Earth. I'm going to go ahead and copy these headings over because I think these are the only headings we're going to use here. If we had some problems, you might have some problems where we have 3 or 4 columns, but this one's going to stay pretty simple, and we're only going to use the 2. All right, so here, our puck is slowed down. In fact, our puck has half the original speed, half the speed than it did have, but it's also gone uphill. So we have less energy stored kinetically, but we have some energy stored gravitationally. So the energy stored kinetically isn't as big anymore. I'm actually going to drop it down to 1 box. I'd be fine if you dropped it down to 3 or 2 boxes. But we know that the energy stored kinetically has dropped. Why? Because that energy that used to be stored kinetically is now stored gravitationally. So all the missing boxes are now over here. Again, I don't care how you split it, but some of the energy that was stored kinetically needs to now be stored gravitationally. Finally, I don't have any kinetic energy stored over here because it's not moving anymore. So I'm just going to leave that one out. All of the energy that used to be kinetic is now gravitational. So I'm going to have all 4 boxes here. So this is a pretty decent setup for our LOL diagram. This is 99%. Like, this is probably what you should use. Just though, because I'm trying to future-proof this particular video, there will be some problems where this is not what we want to do. So what I'm going to do is I'm going to copy it, and I'm going to show you a slightly different version of the diagram but use a different system. So we could not include the Earth in our system and just have the puck. And let's think about what that does. And that's actually a really important question. If we choose the system as just our puck, no Earth now, a lot of stuff is the same. There's still energy stored kinetically to start. And that's fine. That's not going to change. That's going to start off high with 4 boxes, and it's going to drop, and then it's going to drop to 0. The problem is this, is that energy is no longer, we can't say is being stored in the system anymore. Remember, energy stored gravitationally is energy stored between the Earth and the puck. And if we're not including the Earth, that means we can't include that energy. So we can't include it. It cannot be gravitational, which means that that energy is no longer in the system. Instead, that energy is leaving the system as work. So it has the same effect. It has the same effect on the puck. The puck is still slowing to a stop, but the way we think about it is different. Here we think about it, well, the puck still has the energy, it's just stored in the gravitational field between the puck and the Earth. It's still there. Here we say, no, puck doesn't have the energy anymore, it gave it away. Where did that energy go? I don't know. I don't care. Sometimes this is appropriate. Sometimes we just know that the energy is gone and we don't really care where it goes, in which case you can get away with just saying, oh yeah, it left, work, done. Sometimes, like in this problem here, we're probably going to care about exactly where that energy goes and how it's stored. So, long story short, this is a valid way to do the problem, but probably not the way you should do it for here. Actually, the problem is solvable this way, though. You could calculate how much work would have to be done to slow this to half speed, and then how much work would have to be done to slow it to full speed, and then calculate how much work it takes to lift things and to what height you could lift it. You'll ultimately get the same answer, but I think it's going to be easier for us to think about this in terms of energy stored gravitationally than it is for us to think about things in terms of work. So they both happen, they both are valid. This particular problem is, I'm going to go with this. So we have a few questions here. The question number 1 is, how much energy is stored in the puck initially? Well, when we look here at our LOL diagram, the only way we're storing energy initially is kinetically. So the kinetic energy we know is from our notes by looking at we did some algebra and actually used some of our old equations and combined it with our definition for work, that the energy stored kinetically must be 1/2 the mass of the object times its velocity squared. So in this particular case, 1/2 times 2 kilograms times its velocity, 10 meters per second, squared. This ultimately will end up getting us 100 joules of energy. So initially, our puck has 100 joules of energy. I'm even going to mark that up here. You do not have to, but just to help us keep track of it, we know that this is all the energy we have to start with, is 100 joules. Well, halfway up, it doesn't have 100 joules of kinetic energy anymore, does it? Because it's not going as fast. Now it's only going 5 meters per second. So here, I'm going to go ahead and just do my same exact equation again. The energy stored kinetically is 1/2 the mass times the velocity squared. But now things look a lot different. 5 squared is 25, 2 times 1/2 is 1. So this just turns out to be 25 joules. We only have 25 joules stored kinetically now. This, by the way, is why I only put 1 box, because I knew that we only had 1/4 of the joules that we started with. So this is only 25 joules over here, which means this must be 75 joules. We still have to have 100 joules to work with, but it's just stored differently. Conversely, if you're doing this version of the problem, we would have started off with 100 joules, and this would have been 25 joules, which means we would have had to have done 75 joules of work. Which, again, there will be problems where this is the better way to do it, but this is not one of them. Finally, we are going to move over that last 25 joules and we will end up having 100 joules all stored gravitationally. So how do we get the heights here? Well, again, from our notes and from our definition of work, we know that the energy stored gravitationally will be equal to the mass of the object times our gravitational field strength at 10 newtons per kilogram, times however high you lift it, how far you pick the object up. So if we know that if we know we have 75 joules here, that means 75 joules, let's move this, let's try this a little bit nicer. 75 joules will be equal to the mass of the object times our gravitational field strength times the height we lift it, which means that the height we end up lifting it will be equal to, if I can do the math in my head correctly, 75 over 20 meters. I'll go ahead, throw that in my calculator that I still haven't figured out a good way to show you. Yeah, and we end up getting 37.5 meters. So a pretty big ramp. We are 37.5 meters in the air at this point. That is the only way that we can have 75 joules worth of energy stored in the puck. So this one must be 37.5 meters. Again, you could have done this with work. With that much work, you could lift this puck 37.5 meters. The math will work out the exact same way. Totally acceptable. All right, last but not least, now all 100 joules are going to be stored gravitationally. So I'm going to go ahead and do the same exact math I did before. Now if we have 100 joules stored gravitationally, the 2 kilograms times our gravitational field strength times the height. So I just get 100 divided by, oh, sorry, am I doing that wrong? Did I do that wrong? Sorry guys. Yeah, I did that wrong, my bad. I moved the decimal point. I'll leave, you know what, I'm going to even leave that in the video so that you can see I make dumb mistakes all the time. Correction, I shouldn't say a dumb mistake. That's a normal mistake. Anyhow, so 3.75 meters. And then here, if we're going to solve for this height, we end up getting a height of 5 meters. So this ends up being 5 meters. We'll go ahead and fix that. All right, so to review, we have sort of kept track of how energy is being stored between the puck and the Earth. Initially, all that energy is being stored in the puck kinetically, but as it goes up the ramp, more and more of it will be stored in the gravitational field between the puck and the Earth. And all we do is we do our calculations. Now, if you wanted to, you could do this same exact problem using our stuff from Unit 2, and I promise it will not be this short. This saves us a ton of time and a ton of energy solving this problem, especially because I didn't give you the angles. Yeah, like I didn't give you any of the distances. You're going to have to find all that out yourself. It's doable, but I highly recommend using this properly. Anyhow, so sorry, let's just highlight everything here. The final answers are, it will be going half its original speed when it's actually 3/4 its original height, 3/4 its final height, and then it'll be at its final height once it reaches this 5 meters once it reaches no speed. Has 100 joules to start off with stored kinetically, but we move that over gravitationally. You could have done the same exact problem by describing how the energy is leaving the puck and is now being done as work, and that work is actually being used to pick up the puck. But again, that's only if we're including the Earth in our system can we use this EG. Otherwise, we have to just use work. All right, everyone. So I will post this key. I will try to annotate it and give as much information as I can. Do let me know if you have any questions about how any of this goes. It's okay if the first 8.1 assignment didn't go great, but ladies and gentlemen, I would love to have you done like for the year ASAP. So maybe this first one doesn't go great, but then let's get this one down and be perfect at them. I would love it. Let me know. Stop by office hours. I'll be around. All right, everyone.